the holonomic brain theory is based on some insights that Dennis Gabor had. He's the inventor of the hologram, and he obtained a Nobel Prize for his many contributions. He was a mathematician, and what he was trying to do is develop a better way of making electron micrographs, improve the resolution of electron micrographs. And so for electron microscopy, he suggested that instead of making a photograph, essentially, not with electron microscopes, we make photographs but using electrons instead of photons. Right. And he thought maybe instead of making ordinary photographs, what he would do is get the interference patterns. Now, what is an interference pattern? When light strikes or when electrons strike any object, they scatter. Mm-hmm. But the scatter is a funny kind of scatter. It's a very well-regulated scatter. For instance, if you defocus the lens on a camera so that you don't get the image falling on the image plane, and you have a blur, that blur essentially is a hologram. Oh. Because all you have to do is refocus it. So
contained in the blur is the actual image.
That's right. And, but you don't see it as such. And so one of the main principles of holonomic brain theory, which gets us into quantum mechanics also, is that there is a relationship here between what we ordinarily experience and some other process or some other order, which David Bohm calls the implicate or enfolded order, in which things are all distributed or spread. And in fact, the mathematical formulations are often called spread functions that spread this out.
Now, what you're talking about here is the deep structure of the universe, in a way, beneath the subatomic level, virtually.
That's right.
Of matter itself are these quantum wave functions, so to speak, and they form interference patterns. Would I be wrong in saying it would be like dropping two stones in a pond, the way the ripples overlap? And is that like certainly an interference?
That's certainly the way interference patterns are made.
And you're suggesting that at that very deep level of reality, something is operating in the brain itself.
Well, no.
Okay.
In a way, that's possible, but that's not where the situation is at the moment.
Okay.
All we know is that the mathematical descriptions that we make of, let's say, single-cell processes and the branches from the single cells and how they interact with each other, not only anatomically but actually functional interactions, that when we map those, we get a description that is very similar to the description of quantum events.
When you take into account that there are billions of these single cells operating in the brain.
And the connections between them. So there are even more, there are trillions of connections between them, and they operate on the basic principles that have been found to also operate at the quantum level. Actually, it was the other way around. That the mathematics that Gabor used, he borrowed from Heisenberg and Hilbert, who developed them first in mathematics for Hilbert, and then Heisenberg used it in quantum mechanics, and then Gabor used it in psychophysics, and we've used it in modeling how brain networks work.
So, in other words, in the brain, when we look at the electrical impulses traveling through the neurons and the patterns as these billions of neurons interact, you would say that that is analogous, I suppose, or isomorphic to the processes that are going on at the deeper quantum level.
Yes, but we don't know that it's a deeper quantum level. I mean, in the brain, it's just it's analogous.
That may or may not be the case.
Yeah, analogous isn't quite the right word. They obey the same rules. They obey the same rules. It's not just an analogy, because the work that described these came independently of. See, an analogy would be that you take the quantum ideas and see how they fit to the brain, the data we have on the brain. And that's not the way it happened. We got the brain data first, and then we see, look, it fits the same mathematics. So the people who are gathering these data, including myself, weren't out to look for an analogous process. And I think it's a very important point, because otherwise you could be biased, and there are lots of different models that fit how the brain works. But this is more based on how the brain was found to work independent of these conceptions.